before, I hope I am not, I'm not trying, as I said, to discourage any one of you of AI4NETS. On the contrary, just to say that we have really a very interesting field for the next years. So if you were thinking on jumping into machine learning, AI, and apply it to networks, I think it's really the right time. And even before going into this last comment, even though the AI or machine learning community might not be that much interested in some of the applications we deal in networks, networks by themselves are extremely important for the core of everything that is machine learning. Just think, for example, about data centers. So one of the, let's say, since a couple of years, performance in data centers, scheduling in data centers, how to, let's say, even transport protocols within data centers is a very hot topic. When you think about doing machine learning at scale, where you have to, let's say, have huge clusters of data, moving data from here to there, the networks themselves play a critical role. So, of course, there are more and more, let's say, interest from the machine learning community in trying to match the, let's say, the applications themselves, or the learning applications themselves, with the networks themselves in the terms of performance in order to provide these things. But even if you go now to other topics like federated learning, edge computing, and so on, again, the success of AI and ML will 100% be linked to the performance of all these networks and the architectures that we, as networking people, are able to deploy. So imagine applications where actually part of the computational power will be in your end devices, but then, of course, part of the computation will be at the edge of the network, where you will be centralizing different type of learnings and so on. So there are also lots of topics that are super hot topics where, yes, the machine learning community is paying a bit more of attention. So at the end of the day, given that machine learning and AI, it's about data, and data cannot be fully centralized in any place, you need the communication network to actually allow all these things flowing. So even concepts like, I would say, distribution of knowledge networks are things that are very interesting for us. So just to say, I think we as networking people, we are really on a very interesting time for this. But okay, enough of the chatting. Let's go now into some applications, and I will just start first with some application of deep learning for malware detection. And the idea here will be to try to avoid feature engineering. So let's see what is that, and yeah. Okay, going now, this is just a small introduction, but in general, I tend to say that, this is not fully true, you have to read it in between the lines, but I tend to say that artificial intelligence itself is as smart as a donut, or that actually machine learning is still stupid. Of course, it's not the case. There are many advancements in recent years, but I think that really the big revolution that we have seen so far, it's on two specific things. It's on the big data processing capabilities and on the availability and accessibility to data. Let's say machine learning benefits are basically linked to the ability of machines to do some things that humans we cannot do. And in particular, what machines can do that we cannot do is that they can handle large amounts of data because they can compute lots of math operations per second. Humans, we cannot do that. And the machine learning algorithms, they can basically work in high dimensional spaces. So imagine us humans, we can barely live in a 3D space, 4D space, taking into consideration time, but we cannot handle so many dimensions at the same time. And these type of things are very easy for a machine, right? For you, define a vector of dimension 10,000 is the same. Of course, there are some complexities there, but for the machine, there is no big deal. So, of course, you have the big benefits of machine learning. If you couple that with big computational power and the availability of all the data that you might want, voila, you can have lots of, let's say, improvements in performance. But the truth is that the algorithms are still very far from what we call a real intelligence, right? Or a general intelligence. Because imagine, for example, just very simple logical relationships. You will still need lots of data and lots of computational power to actually learn them. Whereas for us, for humans, this might take actually no efforts at all. So yeah, I mean, I try to say artificial intelligence and machine learning, yes, they are improving strongly. Every second day we have new improvements that are really revolutionizing the space, and this is very good. But still, these things are not what sometimes the media is trying to sell or to, let's say, show us a super hype in intelligence and so on. So regarding learning, you can discriminate or separate learning by the two paradigmatic approaches that we have, shallow learning and deep learning. Shallow learning is what traditionally we have been doing for the past, I would say, I don't know, 60, 50, 60 years. It's much less about, let's say, the data itself, but it's much more centered on human expert knowledge. And the whole point on shallow learning is about feature engineering. So imagine, for example, you want to have a system that wants to classify between women and men, and you use as a feature the colors of the eyes. Of course, with that feature in mind, it will not work. You cannot differentiate men and women because of the color of the eye. It's very difficult, right? So if you actually do a better feature engineering and you have an expert that really explains or understands the difference between men and women, can really say, okay, which are the specific features that can separate between these two classes? And by just using those features, a model can be very simple. I can just use not that much data to actually find which are, let's say, the borders between those features, and then that's it, we have our model. So shallow learning is what we have been doing so far, and it has been super successful. But of course, the problem is that you require lots of expert knowledge to define the features. So in shallow learning, features are everything. On the other hand, the deep learning is the big revolution in which you can be a complete outsider of a domain that you barely understand what is the data about. You can barely say, okay, I'm not expert in these fields, but you have lots of data describing the problem. So lots of data describing the inputs, output. And the deep learning is about what we call automated feature engineering, or in a more general case, the representation learning, in which part of the algorithm itself, or part of the approach, is to learn which are the best representations of the data that we want to analyze to actually perform the specific task, right? So basically in deep learning, you will use big amount of data to actually understand which are the features that describe certain element to actually achieve the performance of your specific task, right? What we are going to see now, it's an application of exploring deep learning to try to detect malware using network traffic. So very simple, let's use deep learning to do the following. Okay, sorry, this is actually what I was saying about shallow learning versus deep learning, but okay, I mean, more of.
Sorry, you are muted.
You are muted. You are muted.
Sorry, thanks for saying. I've been talking like. Sorry for that. I thought I had unmuted.
No,
Shit.
it was just for a few seconds. Don't worry. You were muted just for a few seconds.
Okay, so probably I pressed something. Okay, so hopefully you follow me to some extent. Did you hear the part of shallow versus deep learning?
Yeah, you went muted at the beginning of this slide.
Ah, okay, perfect. Okay, so probably I just clicked something. Thanks. Okay, sorry. Okay, so the problem we want to solve is the following. I want to capture network traffic, and I want to say, okay, there are packets here or flows. We will work at the flow and the packet level, and I just want to have a classifier where the task is to say this packet or this flow corresponds to malware traffic, and this packet or this flow corresponds to benign traffic. Okay, and what I will be doing here is to rely on a fully supervised approach. So saying I have some ground truth data to train a model, and I will be training a deep learning model, right? So this will be like a kind of example to say. So the first thing when you're going to to, let's say, start your deep learning architecture design and so on, is to first think on the representation you are going to consider for your raw data. So whatever you consider that will be the element that you analyze, it's what we call the raw data itself. So for example, in an image, the raw data itself are all the pixels of the image that you want to analyze, right? So a decision to actually analyze an image could be to say, okay, I grab all the pixels, and those pixels will be the input to my deep learning model. But you might want to take some other kind of decisions and say, okay, instead of grabbing all the pixels by themselves, I will just group pixels and say, no, I will, instead of putting independent pixels, I will enter to my model blocks of pixels as input to the data. So in our case here, we are dealing with basically packets and flows, and we have to decide which is the representation that we're going to feed into the deep learning model. So I will be using two representations to actually do this malware classification at the packet and at the flow level. When I work at the packet level, I will basically say, okay, what I will be feeding to the deep neural network for this problem is the first n bytes of every packet, right? So the representation of a packet for me will be the first n bytes of that packet. So whenever I have a new packet, I will just keep the first n bytes of that packet, and those n bytes, I will feed them to my network. Of course, if the packet has less than these n bytes, I will be doing zero padding, so I will just complete the missing positions with zeros. And if this packet has more than n bytes, I will be just cutting the packet to the first n bytes. So that will be the input for my neural network when I'm just using packets. When I am using flows, I will use something very similar. That is, I will just keep for each of the flows that I'm having, I will keep I will use a sort of matrix representation where I will keep the first n packets of the flow, and from each of these packets, I will keep the first n bytes. Okay? So those are basically the kind of first representations for my raw data. But besides that, I will make no assumptions at all about the data. So for me, the data is just bytes flowing through the network. Okay? When those bytes are aggregated into flows, I will say, okay, the representation are the first n packets of the flow, and I always keep the first n bytes of the packet. So having this in mind, what I will do is to create a deep learning architecture where I will basically try to use some ground truth data to basically identify either at the packet or at the flow level when there is a malware or when there is normal traffic. So we will see later on which are the, let's say, the core layers that we use in any deep learning architecture. But actually, sorry for, yes. But in general, we will see that we have two core layers that are used let's say, in any kind of deep learning architecture. Normally, we have convolutional layers or recurrent layers. So when we talk about convolutional layers, the idea of the convolutional layers is to basically extract spatial representation or spatial information that is inside the data that we are analyzing. So when I talk about spatial information, it's correlation that happens into the, let's say, at the same time of the data that it's actually coming in. So I'm not considering, you consider one single sample, you will see correlations that happens between elements of that specific sample. So for example, in the case of I am analyzing bytes of the packet, the convolutional network, given one packet and given the first n bytes that I'm keeping, will be able to capture correlations among all those n bytes that I am analyzing. Okay? So it's something that happens only at one instant time. But then, of course, in deep learning and in neural networks, we have what we call the recurrent layers. The idea of recurrent layers is to actually try to exploit the ideas that data might also have some sort of temporal dependencies, and one sample at time t might also depend of what we saw in the previous 2, 3, or let's say 5 samples that I've seen before. So you will see that actually in other deep learning architectures, you will have recurrent layers that are used for other type of applications. So you will always see that these are the kind of two core layers of deep learning. At least, let's say, until some months ago or some time ago. We will see that this might rapidly change. Besides actually these kind of layers, we have other type of layers that are what we call like helping layers that actually help us to better train these networks. What's deep learning? Basically, deep learning, it's the idea of actually grabbing many layers of these convolutional or recurrent layers and so on, and put them all together, one after the other one, in such a way that by having a very complex architecture, I will be able to capture the complexity of the problem I'm trying to solve, right? The whole complexity of deep learning is actually how to train those models, because normally those models, they have lots of features. And what we have actually is that we have different type of supporting layers that actually help us in better training those type of networks. We will see this in full detail next, but you will see layers like batch normalization. You will see layers that are like dropout. For example, things like a dropout layer, what you try to do sometimes is to try to do averaging on the training of the model by basically having some layers in which you connect some neurons from one layer to the other one, but from time to time, you just make some of those neurons disappear. So when you're learning or when you're training your system, from time to time, some of those networks, some of those neurons, you will turn them off in such a way that you avoid that your model gets focused too much into some specific thing. But yeah, I mean, this is basically the overall architectural principles that we have in any kind of deep learning system. But as I say, we will see it more in detail next. Okay. So using this type of ideas, what we do here is we have already the representation for the bytes, for the packets or for the flows. Let's try to build a deep learning architecture so that we can use it for our classification task. So we first start by the packets, the deep learning packets analyzer. So here, as I was saying, the input to this is the first m bytes of a packet. Here I am keeping all the different parameters here are set based on trial and error. But basically what we do is that we keep the first 1024 bytes of a packet. And this is basically the entrance, or let's say the input to the neural network. So in my deep neural network, I will have one vector of dimension 1024. That is what I feed into the network. Then what I will be doing here is actually to concatenate different layers of the previous layers that I showed you before, so that I will make the deep learning architecture powerful enough to be able to capture the relationship that it's between these input bytes and what I see at the output as normal or malware traffic. So in particular here, I will not go into the details, but we have one-dimensional convolutional layers. So actually we have two of them. We have a max pooling layer. I will then explain what's a max pooling layer, but it's just something to reduce a little bit the dimensionality. We are actually here also having something that is a recurrent layer, that is this LSTM. We will see what are LSTMs, but it's actually something that we are adding here to capture temporal dependencies. And then basically what we have is a kind of fully connected standard network that allows me to go from the convolution layers to the final output. So let's say at the end of the day, we build this kind of complex architecture. In this architecture, there are many parameters to train. Then using the ground truth data, we train it and we see how good it performs. When we do the same thing at the flow level, here at the flow level, as I was saying, the input to the model is not a vector, but it's a matrix. So it's a matrix where we were keeping the first m packets, and for those m packets, the first m bytes. Here we take an approach that it's, let's say some time ago, maybe you know, when we were doing traffic classification, we discovered that for doing traffic classification, by just analyzing the first few packets of a flow, we had enough information to discriminate between applications. Why is that? Because actually the applications at the time of doing the the handshake, so the establishing of the communication, they were having a very distinctive pattern. So here we took a similar approach. We took just the first 2 packets of every flow and the first 100 bytes of every of these packets. We consider a similar architecture. The architecture here is a bit smaller, just because at the flow level we have much less data than at the packet level. And at the end of the day, we build our network. Actually, to build this, for example, as I was saying, you can use some stuff. If you're, let's say, very used to programming in Python, you can just use PyTorch libraries where you already have all these type of layers pre-implemented, and it's very easy. Really, it's very easy to interconnect these things. And basically, once you understand what each layer means, it's very easy to build your own architecture. Okay? So, of course, normally when you are building an architecture, you follow architectures that have proved good performance in the past and so on. But okay, here we have built our architectures, and then it comes to the idea of saying, okay, let's evaluate these. So for doing this, actually, the implementations were done on TensorFlow. What is this? Is the loss function used to quantify the prediction? Yes, yes. Actually, the function loss is what you use when you're going to train your model. Actually, what happens when you have supervised data in any kind of supervised learning approach? What you want to do is that you tell the algorithm, hey, this is the input, and for this input, I want you to provide this output, right? Because you know the ground truth. And then you pass that input through the whole system for doing the specific training approach. We will see what the training means in deep learning. And then you have to quantify the error that you got at the end, so as to say, okay, actually, I am converging to something that is providing good performance or not. So at the end of the day, yes. Here in the, given that it's, I don't know if I said it, but here actually, as we are using the classification, the task here is classification. I am using, and it's just 2 class, I am using a binary cross entropy as loss function. Okay? But I mean, you can use when you're doing, for example, things more like regression problems, you can use a standard mean square error and whatever you might have. Of course, the error function also is one of the things that you have to decide for your architecture and your model. But okay, let's go on. So here we did everything in TensorFlow. We are using open datasets from there is a project from the CTU University in Prague. It's called the Stratosphere project. So there, it's very interesting that you have lots of, let's say, packet and flow data that it's labeled because it's basically synthesized data. They basically mix, let's say, benign data or data that is captured from normal behavior systems with data that it's, let's say, synthesized from running specific malware attacks. And there you can basically do all your comparisons. What we are doing here is to compare our approaches to a traditional approach that you might use for doing detection that would be something based on a random forest. So actually, if you consider shallow learning models, normally random forests are among the top performing models always, specifically in networking. Because decision trees are super powerful. They have lots of properties, like they are super fast, they are immune to noise. By default, they perform feature selection and so on. And when you couple this with a random forest where you're actually doing an ensemble of decision trees, you really get, let's say, very good results in many applications. So here, actually, yeah, we were saying, okay, let's compare to this, using, in this case, as input, the same, let's say, inputs that are used by the deep learning model. So the raw bytes that we are using. So here, when it comes to the comparisons, we were just detecting 10 different types of malware. I'm sorry, okay. We were comparing here 2 different type of, 10 different malware types. Here you see the ROC curves. So basically here you have the true positives rates and the false positive rates. And this is the comparison between the deep learning approach and the random forest. What you see here is that this is working at the packet level. Even though you can achieve a slightly better performance with deep learning, the performance improvements are not significant, and both of the approaches are not working very well. So I would say that here, if you would like to work at the packet level, what we were trying to do was not really becoming was not really providing any big advancement, I would say. And this, of course, is clear because when you work just at the packet level, in principle, you will never want a model to work at the packet level because cannot scale to run in reality, right? But you are missing, let's say, some kind of information between consecutive packets and information like that. When we then did the same thing working at the flow level, here we see on the right side, we see again the true positive, the ROC curves. Here again, we have the comparison of the deep model, so the raw power is called, against not only the random forest, but also other traditional shallow learning models. And here you see that, yes, at the flow level, the deep learning approach really performs significantly better than shallow learning. Of course, this is shallow learning, but using an input that has no feature engineering. But still, here you see that, okay, by just analyzing the bytes without having any idea of what the features could be, using a deep model, you can actually achieve very good detection performance for this type of problem. When you just, this is something that we were also saying, if you compare your deep learning approach against a system that use domain expert features. So let's say traditionally you will have a shallow learning model where you define very, very well which are the expert features that you will input to your shallow learning model. So in this case, you see that the red dotted curve is a random forest using deep domain expert features. You see that the performance of both models are barely the same, so they are very comparable. So the main conclusion that you can get from here, and it's the interesting part, is that using deep learning, here analyzing just packets and flows at the byte level, you can achieve similar performance to what you could get by using heavily, I would say, handcrafted or domain expert-based features. So even though this application is particular for detection of malware, this type of approaches, I wanted to show this example because it gives you some ideas of how you could actually just analyze bytes on the packets. So you're just seeing packets in the network and you're seeing flows. How can you analyze that without defining any kind of features, just injecting that into a network and being able to do something that can perform very well? Okay, so this is an example of saying, okay, we can use deep learning to try to avoid having an expert that defines specific features to detect or to tackle the specific problem. Of course, again, if you're not familiar with deep learning, everything I said before about the layers will be clear in some minutes. I would like to go into another application that I think this application is very interesting. This application, it's something, let's say, quite critical for us in networking because it's about the idea of making artificial intelligence explainable. And explainable means that if the things are very difficult, if the models that you are building, let's say, let's go back to the previous example. I show you the results, but to tell the truth, I don't know when I go to the deep learning architecture. So I go to this architecture. This model tells me, okay, you know, this flow or this packet is a malware. But I have no idea of why the model is telling me that. I have to trust the model because the model actually, let's say it's a black box. So for me, it's very difficult to understand in this whole architecture, where were the things that were getting activated that were actually telling, okay, this is an attack and this is a normal traffic. So given that this is a very complex model and I cannot fully trust it because I don't fully understand it, for me it could be a bit critical to say, hey, this box is telling me that this traffic is malware, I just cut it. Okay, but maybe it was not malware because, I don't know. I mean, the model decided, but yeah, maybe there was some bias in the data, there were some problems, and I couldn't know exactly why the decision was being taken. In the same application, if I was comparing to the other approach, to the domain expert features, I could, let's say, use the random forest, and the random forest could tell me, hey, this is an attack, and I can just, let's say, look at the structure of the random forest and get back to say, okay, which were the features that were leading to this specific decision. For example, the domain expert features might be that, let's imagine that one of the features was packet size. And maybe the algorithm tells me, you know, this is an attack because actually all the packets, they have a size that is below, I don't know, 100 bytes to say something. So this could be something more coherent, saying, oh, okay, you know, this can be malware because maybe this is some traffic that there is no content at all, and it's just something that is trying to, I don't know, open some connections or do something that might, lead to an attack. So this is why actually the deep learning itself helps you in providing things that can work more autonomously, but they become very difficult to, let's say, explain. So for all this, there is a field that is called explainable AI that basically tries to interpret the decisions that a model is taking. So as I was saying, machine learning models, when we talk about, let's say, deep learning in particular, but we might say in complex models, they are like black boxes. So for example, if you know SVMs, SVMs can also be considered as black boxes because sometimes it's very difficult to understand what the model is doing itself. So in general, the problem is that for us it's difficult to understand why the model takes a decision, and this, at the end of the day, what happens is that we decide not to use the model. So part of adopting or not machine learning means that I have to trust what these things are doing, right? Okay, so explainable AI provides approaches that are capable to explain models and to explain individual predictions by somehow tracking back to the inputs that were leading to a certain output. Okay? So basically, okay, this is just an example of saying, okay, if you consider all the families of models, the more complex a model becomes, the more difficult it is to explain what the model is doing. Of course, the advantage is that the more complex the model becomes, the more expressive that model becomes, which means that the performance normally in your specific task is better. So if, for example, you would like to resolve a specific, let's say, natural language processing problem using linear regression, maybe there it will be impossible to achieve any kind of minimal solution, whereas with deep learning, you might, let's say, achieve pretty good results. So yeah, I mean, there is this trade-off between explainability and complexity or performance, right? So what we would like to have is something to say, okay, even if the model is very complex, at least when the model tells me some kind of decision, it's capable to tell me why the model is taking this decision. Okay, and here I have a very simple example that it's easy to understand. This is, imagine, for example, nowadays in health, we are using lots of machine learning, not to take decisions, because of course the decision has to be taken by the doctor, the expert, but we use machine learning to use as a kind of assistant to analyze different data from one patient. Could be images of, let's say, X-rays, different type of studies and so on, and to try to give some kind of hints or diagnosis, right? So imagine that we have a model that basically tells me if my patient has a flu or not. Okay, this is nowadays this is very popular with COVID. Imagine that this model is trying to predict if the patient has COVID or not. And in this case, let's assume that the inputs to these models are these simple inputs like sneezing, the weight of the patient, if the patient has headache, if the patient has fatigue or not, and the age of the patient, right? So this is the kind of data that it's input. What I would like to have is a type of system that tells me, okay, there is a patient, I see that this patient has this type of inputs, he's sneezing, he has a certain weight, I don't know, he has a headache, he has no fatigue at all, and he has this certain age, whatever. I would like that there is something that tells me, okay, if the model is telling that this patient has a flu, the model will tell me, okay, this patient has a flu, and I'm telling you that he has a flu because the patient is sneezing, the patient has a headache, and the patient has no fatigue. So me as an expert, I understand those features, and I can say, oh, okay, this makes sense. Makes sense that if a patient is sneezing and has a headache but no fatigue, has a flu. So me as a user, I can rely on that model to give me some kind of, let's say, second diagnosis opinions on, okay, is this patient actually having a flu or not? Okay, the thing is that normally the model that you might have here to do this could be very complex. And what I would like to have is this, what we call an explainer, that will be another type of model that helps me in providing this type of explanations that could help me. So when it comes to explainable AI, there are lots of approaches that one could follow. It's a very interesting domain, full of things. I can send you, if some of you are interested. I mean, I didn't say it, but whenever, if you're interested in some specific things, drop me a line and I could potentially guide you into some directions with some papers and stuff like that. When it comes to explainability, there are many interesting approaches. I will be showing you one that is very popular, that is called LIME. So the LIME approach actually helps in building an interpretable model that basically is locally faithful to the model that we are analyzing. What does it mean locally faithful? Is that I have a very complex model that basically takes a specific decision, and I would use LIME to build a model that in the region of that decision for that specific input behaves locally exactly or very similar to the complex model. Okay? So the LIME approach, basically, it's an explainable approach that helps in explaining individual decisions of a model. So if I have, let's say, my deep learning architecture, for this input X, if the decision is Y, my LIME explainer will tell me, okay, the decision is this one, and these are the reasons. But the LIME will not be able to explain why the full model or how the full model is working. There are other approaches, for example, other approaches like SHAP. SHAP is it's an extension of LIME, but that goes into a, let's say, more interesting dimension that tries to do a more global explanation of the model, so that you could not only say, okay, why the model is taking this decision, but why the model is performing like this or like that. Okay, but it's a broad domain here that is very interesting. Okay, this I will just, is what I was saying, that what we would like to have, the explainer can explain us what's going on. These are properties of what you would like to have of an explainer. But let's go into LIME, into explainability, to understand a little bit how it works, because then I will give you some examples. Let's imagine the following. So there in the picture, we have a classification. Let's assume we have a very complex classification model that is classifying inputs in two colors, red and blue. Okay, so given an input, there are two classes, the red class and the blue class, and the model is very complex. It's so complex that this, you see basically there you have like a border between the two classes. The border is something very nasty, yeah? There is this shape that is whatever, okay? So imagine that now what we have, yeah, is the specific, there you have one bold red cross, yeah, that we want to, let's say, explain its decisions. You see there that the model for that bold red cross, the model decided that it belongs to the red class. And I want to understand why the model, the complex model that has this border, has decided for that. What LIME will do, in a nutshell, is just basically say, okay, in the surroundings of that sample, I will basically linearize the model, the decision boundary that I was taking, that was very complex. I will basically approximate it by something that is easier to understand. For example, a linear discrimination model, right? So what would mean here is that if we call F, here we are calling F at the complex model that we want to explain, and G, this local model G, will be the simple model that will be able to basically provide a similar kind of decision to the complex model F, but only in the surroundings of the specific sample that I want to explain. Okay, so how do I do this? Basically, I do it in a very smart way, because LIME is also model agnostic, which means that this LIME approach can be used for whatever type of model you want to use. You don't need to, LIME is not only applicable, I mean, LIME basically can be applied to any kind of model. And why is that? Because the way that LIME builds this local linearization is doing it by learning. It's not actually trying to linearize the model, knowing how the model behaves. It's not that, okay, he has a function of the complex model and tries to linearize it. No. What basically does is the following. It basically draws samples in a kind of random manner in the vicinity of the sample that you want to explain. Yeah, so for example, what it basically the model does is that it samples instances, here in this case I call them seed, around the X sample that I want to basically explain. And using those samples, I mean, I use some sort of similarity measure just to sample things that are in the vicinity of X. Because I just want to have samples that are really, again, this has to be only local. So I don't want to generate samples that are very far from that point, because if then I build a new model using samples that have nothing to do with this, it will not work. So it basically uses some sort of similarity measure to outweight samples that are randomly taken very far from the point that I want to explain. And then what I do is I have these seed samples, and I label these samples with the complex model that I want to use. So basically, what I will have is, as input, the sample seed, and as ground truth for those, I will have the prediction of those sample seeds using the complex model F. So using basically the set and the F of set, so the random inputs and the label of that, I will just build an interpretable model, for example, just a linear regression model around that sample. And that will help me basically in explaining if I have a linear function separating these two things, it's very easy to understand which are the features in this kind of linear sample, in this kind of linear model that are basically putting one cross on the red side or the cross on the blue side. And this is basically the whole trick.
I've got a question before you go on to the next slide.
Yes, please.
Can you go back to that picture, please?
Yeah, sorry. Yes.
Okay, it looks to me as though you're using a subset to define a support vector machine. There's this dashed line that's slightly off the vertical that's dividing the blue blobs from the plus signs. And if you were to include a plus sign far to the right of the picture, there are two small ones all the way over in the rightmost lobe, pink lobe, then the support vector machine wouldn't work, right? So are you localizing by building a support vector machine that specifically discriminates between the blue blobs and the plus signs?
I mean, it's not that I'm building a support vector machine, but I mean, in any case, what I'm trying to do is to only consider those samples that are in the vicinity. So exactly as you say, those crosses that are appearing there in very far positions, I will not even consider them, because I'm using this similarity measure, that it's a kind of distance that will weight those samples that are taken very far with a very low weight. So those samples will not be considered by my model.
Right.
And what I do is I use those samples that are in the vicinity, so that they have some strong weight, to build whatever type of local, linear, or let's say explainable model that I could use. I don't have to build there a linear model. I could use, for example, a decision tree. I could say, in the vicinity, using only those samples, I will build a decision tree, and I can say, this decision tree performs very similar to the complex model I want to explain, only in the surrounding of this sample. And because of that, I can use that decision tree to understand which features are leading to this or that decision.
Right. But the problem is that the model's a black box, so you don't know what makes blue blue and pink pink.
Yeah, no, but exactly. This is exactly what I want to do. What I do have, the only thing I have from the complex model is the function. I have the model. So even though I don't understand the model, it's a black box, I can put in a sample and the model will tell me which is the prediction.
Right. It's very nice for classification, but it doesn't tell you what makes blue blue and what makes pink pink.
Yeah, I mean, actually,
there's no mechanism there.
No, but the mechanism, I mean, the beauty at the end of the day, it will not tell me what makes blue blue and pink pink. It will tell me for this specific X red cross why you decided it to be on the red class.
Oh, okay, it will. Okay.
But only for this one. It will not tell me in general why you decide things for blue or for pink. totally right. But in
Okay.
the surrounding, where I have linearized this, it will tell me, okay, for that sample, it is red because of this.
So that means that extrapolation is very unwise under these circumstances.
I mean, you cannot extrapolate. I mean, here the example is pretty good in the sense that imagine that we are using this local model that is this straight line, that it's a linear regression model. And I want to use that to explain, for example, what happens in, okay, I will see if I can use a pointer. Oh, let me see. Sorry, cancel. Where is my pointer? Here, annotate.
Okay,
So,
I can see your mouse. Oh, no, that's my mouse. I thought that was your mouse.
no, imagine, I can explain all the points that are here.
Right.
I could explain it. So let's say even for these points, the explanation could be quite fine. But imagine that I want to use this line, right, to explain the point that lies here.
Yep.
It will
That's
be a
harder.
disaster. It will be a disaster because the only way there to linearize it will be to have something like that.
Right.
So this is actually the main problem of Lime, is that Lime can work fine as far as the complex model that I am linearizing, it's quite stable in the surroundings. But if you have this type, for example, Lime, in this case, will be very bad. Will be very bad here, very bad here, very bad here,
Sure.
very bad here. So this is why it provides hints, but yeah, it has lots of issues as well.
Thank you.
No, thanks for the question. So the cool thing, I mean, besides how Lime works, I mean, there is a very nice paper on Lime, and you can then get into explainable and so on. But what I wanted to do with the explainability is to show what you can use explainability for. Remember that at the beginning, at some point, I said, one of the major problems we have with deep learning is that, okay, we don't understand the models because sometimes the model is complex, but also there is bias in the data. And sometimes we don't even understand how to decide by this or that model because we think that, okay, let's decide, I build, let's say, different models. I will choose one because I think that it performs the best according to a kind of, let's say, accuracy. So the best model I have is the one that provides the best accuracy. And this is called totally false. I mean, in some applications, a model that has the best accuracy could be the worst model you are getting. And this is what I will try to show you. And explainability can actually help you in doing these things. So we'll see 3 or 4 examples that are quite interesting. So example 1, we have a task that is about classifying emails. So you're getting emails, you are reading the text in the different fields in the email, and you want to say if this email, okay, this is an example I know, if this email is talking about Christianity or is talking about atheism. Okay? I mean, these are the examples from the paper, so don't tell me why. But imagine you have this application that you want to classify between Christianity or atheism, and let's have we build 2 very complex deep learning architectures that take as input all the words that you have in the email, all the fields, and actually they pass it through many different layers. And you want to say, okay, you have the 2, which of them has better chances to make it, let's say, into a generalizable application for detecting emails between Christianity or atheism. So you come here and you see algorithm 1 actually, before going to this, algorithm 2 in this example is actually better than algorithm 1 in terms of accuracy in the validation dataset. So actually, imagine that you have your system, you are training on one part, you are validating on some other part, you have some other part of the data for testing. When you do the cross-validation, the algorithm 2 gives better results than algorithm 1 in that cross-validation. So you will say, okay, algorithm 2 is better than algorithm 1. I go for algorithm 2. This is the one that I ship into my box. I send it to the customer. He will deploy it. And he will call me 10 minutes later saying, hey, this doesn't work. What happens is that algorithm 2 was extremely biased. And even though it was providing very good accuracy, actually the features or what it was using to classify the mail as atheism or Christianity had nothing to do with Christianity or atheism. So when you see the pictures, the algorithm 1 in this in algorithm 1 basically it tells me when I use the Lime explainer that a certain email that, here is the email, the document that you see. So for example, there's an email here that comes from Paul Darwin that it's talking about David Koresh and about God and blah, blah, blah. So the algorithm one says that this actually document is talking about atheism because sorry, this is atheism. Yes, okay. Because actually it's looking at words like God, at words like mean, and at words like Koresh. So basically, if you consider here the colors, atheism is the violet, right? So it's deciding for this atheism because he understands that the words God, mean, and Koresh are somehow linked to atheism. Don't tell me why. I think Koresh, this David Koresh, was some. I think I looked for that on the internet once. Someone linked to something related to atheism and so on. But okay, there is God and meaning and whatever. But if you go to algorithm 2, that was the one providing better performance, it tells me actually that this model is predicting that this email is atheism because it's looking at fields like posting, host, reply, and NNTP. Okay, so here they send me. He has a cult leader of the branch Davidians. Good. Okay, yeah, exactly. Something on this direction. So actually, it has some correlation with this. But if you consider both algorithms, at least algorithm 1, even if accuracy is worse, is selecting features that have some correlation for a normal expert like us or someone that understands about Christianity and atheism, than algorithm 2 that is just selecting fields that has nothing to do with nothing, like host, reply, and NTP and posting. So here you see the first cool thing of using explainability. Here the models, they were, in terms of accuracy, different, but the model that was providing the best accuracy was actually a model that was highly biased. Okay, because it was probably, in this model, you can say that there was overfitting, for example. The model actually was just learning what this data was having, and probably in this data, there was a strong bias in which all the atheism emails have a similar posting, host, and NTP fields. So first lesson we learned, always accuracy as the best, let's say, criteria for selecting a model is not the one that we have to follow. And explainability can help us in this. Example 2. This was actually very good. Here what we do is the following. We grab a pre-trained model that it's, you know that in deep learning, when you train a model, these very big learning models, you train them with lots of data. Once they are pre-trained, you can put them online so that people can use them as building blocks for different applications. So Google, for example, has tons of data, of course. So whenever they come with some kind of new architecture, many times they make them available. One of these one is a model that it's already an old architecture. It was called the Inception Convolutional Neural Network. And it was basically an architecture that was able to recognize objects in an image. So you were giving an image to the object. Sorry, you were giving an image to the pre-trained deep neural network, and it was telling you what was present in that image. So the model actually, it's a quite strong model. It was trained with lots of data and so on, but you were feeding the model with this data. What's the problem in this data? Is that here you have a dog playing the guitar. For sure, when the guys trained this model, they were using all natural images that they have available in the internet that were tagged, like, okay, this is a dog, this is a guitar, this is whatever. But they probably had very rare cases or few cases of dogs playing the guitar, right? So what happens here is that this is the output of the model. The model actually tells me that in this picture, there is an electric guitar, there is an acoustic guitar, and there is a Labrador. These are the top 3 classes that the models predict with some probabilities. For example, it tells me that there is an electric guitar with 32%. It tells me that there is an acoustic guitar with 24% probability, and it tells me that there is a Labrador, a dog Labrador, with probability of 21%. So one would say, okay, this model is not very good because the model should have told me, as indication, should have told me there is a dog playing the guitar. But the problem here is that, okay, you are trying to use the model to predict something that it cannot actually handle because it has never seen it before. Okay, the model actually, unfortunately, cannot tell you that this is a Labrador playing the guitar. But the model actually performs very well. Why? Because if you use, for example, explainability, you can see which are the pixels that are being used to take each of those decisions that I told you. And the model is using, in order to tell me that here there is an electric guitar, is using these pixels that actually when you see them, it looks like an electric guitar because it's just the chords of the, or whatever this is called, of the guitar. There is an explanation that this is an acoustic guitar because actually in the pixels you see an acoustic guitar there. And the explanation that tells me that there is a Labrador is actually the face of the dog. So here what you can claim is, okay, by probability or by the performance of the model, you might think that the inception is not performing well. But actually the inception works very well. It provides very coherent results. It's just that the model was not able to answer these specific questions. So here the user was actually abusing of the model. You were asking a question to a model that of course was going to answer it wrongly because it couldn't answer that. Right? So again, one of the other learnings here is that explainability can help us to understand the limits of the things that we can ask a model. Especially this happens with models that are not built by yourself. So this is a pre-trained model, so you don't know what was the training data. Okay? So you can use these type of things to understand what's going on. Third example that is very interesting, discover bias data. Right? This is actually very good. Here we had a classification task that we wanted to classify or distinguish between wolves and huskies. So the Siberian huskies are dogs that are very similar to wolves. And I want to have a classifier that you give a picture and tells me if it is a wolf or a husky. Imagine, for example, that it's a security application that is trying to protect your sheep and there is a fence. And when the animal comes, if it's a wolf, it will basically close the fence so that the wolf cannot go and eat the sheep. But if it is a Siberian husky, it might be the shepherd dog, so it will let it in, right? So the classifier has to classify correctly here. But what happened when we trained the model? Yeah, we did a very strong error. Is that our data was very biased. So the problem here was the following. The picture that the classifier was trying to classify is the husky that you see there in picture A. And the model actually tells me that this is a wolf, not a husky. And I could say, okay, the model was very bad because the model didn't manage to capture the intrinsics here. But actually, when you check the explanation, you say, okay, why are you telling me that this is a husky and not why you are telling me this is a wolf and not a husky? You see that the pictures that the model is checking is not linked to the face of the animal, but it's just linked to the background. So what the model is actually seeing is that in the background there is snow, and the problem is that in the data set, unfortunately, there was a strong bias in which most of the wolf images, they were taken in the snow. So what the model learned, was not the face of the animal and the characteristics of the face, but just the background. So the model learned to say, okay, if there is snow, there is a wolf there. So of course, this is completely wrong. Probably it's not the model, the guilty one, but here it's just that your data was biased, was corrupted. And this happens nowadays in everything that, many classifiers that we have, that they have lots of ethics problems. For example, classifiers about gender issues are very bad because sometimes you are using completely biased data. For example, there are some systems that recommend positions to the different, for example, you want to apply to a position and you have a system that recommends you according to your profile, which are the best positions that you can apply to. And there was a paper that actually was saying that actually this was very biased because they were trained the thing with data that was always recommending for men positions that were more linked to technical stuff, whereas for women were recommending positions that were more or less technical stuff and more artistic stuff. So of course, this was very much biased in the sense that this model is replicating what the training data was actually showing, right? Maybe the data that they show, they were having many more technical positions filled by men than by women. But this doesn't mean at all that actually this is the recommendation you have to make. So these are the things that start making the bias in the data, the bias in the model, the ethics, a kind of complex tangle to solve. And of course, it's difficult, but what I would like is that you are aware of all these things. So if you're aware of all these things, when you go into AI4NETS, you will also be able to, let's say, take a step back and see all these things for the analysis of your models. Okay, this was I think the last. This I will skip it. There are two more examples here, but I will not go through them because we are running out of time. And I would like to at least go a bit more into some concepts of learning. So I would like to give you some hints about deep learning and then to do a very fast, let's say, picturing of what's going on currently in the AI ML space. So here, the other two applications, I leave them there for you to check them. One of them is very interesting about what we call ensemble learning. So the idea there in ensemble learning is that whenever you are going to use a machine learning model, instead of sometimes it's difficult to decide between one model or the other, but if you use ensemble learning, instead of deciding by one or the other, you can just combine them, all of them. Because remember that at the end of the day, a model is just like an expert or a filter that comes with some kind of previous knowledge or hypothesis or whatever. So one model will be able to identify or understand part of the problem behind the data. Okay, so some models will be best for some things, but some others for others. So in the best case, if you have lots of computational power and you can run many things in parallel, instead of just taking one, take them all together and do an ensemble. So this is something very interesting. And the last thing, and this one is something that please pay attention to it. It's the last one is about how to do learning on real time. So basically, when we are having these problems of stream learning where data is not offline, but data is continuously changing, the main challenge there is that you will see new data coming and you have to take a decision for each data that comes. And that decision is either to take a classification step or whatever on that step, or to retrain your model based on that data that you still don't know. Okay, so I leave you those two examples. I think they are very interesting to show you also other challenges that we would like to face. So I will stop this part. Let's take a 5 minutes break now, and we do the last part of the tutorial, going a bit more into the learning per se stuff. Okay?
Pedro?
Yes?
Hi. First of all, this is a very, very interesting lecture, so thank you very much. Where can I find more material about the last two examples? Because they are very interesting.
Yes. I mean, all the slides of the lecture are online. Actually, I will send again the link. It will be also at the tutorials page, but here you have my personal page, and there is a pointer to these AI4NETS slides. There are 5 slide sets. Unfortunately, I will just show you parts of some of them, but yeah, you can go through them, and yeah, I mean, there you will have all this stuff. And then if you're interested in something particular, you can drop me a line and I can send you specific pointers.
Okay,
for sure.
Thank you. Thank you.
Good. Okay, so let's do this 5 minutes so that you can take some air, do some toilets, drinking or whatever, and then we go to this deep learning and other learning topics. Good. I will just jump to the next slide set.